Hi, in this lecture I'm going to be talking about how we can classify symmetric matrices into 5 distinct classes, the most important of which being the positive definite matrix. In this lecture we'll kind of cover the different properties of each of these classes and why it's important to know them. This goes with chapter 2.7 of the deep learning textbook, but there really isn't that much text describing these 5 different types of symmetric matrix, but I just want to include it in here because it'll make future topics in this chapter a lot easier to understand and a lot more intuitive. Alright, so let's get to it. Recall in the last lecture we introduced the quadratic form of a matrix, which I basically described as a succinct way to display a quadratic form polynomial with a matrix vector multiplication. So before here we just simply used this matrix S to kind of encode the coefficients that would be in our quadratic form polynomial if we expanded this out. That was the main reason for this S being here, is the coefficients matrix. But now we can actually think of this in a different light. We can think of this matrix S as kind of being the star of the show here, and we can actually just plug in any symmetric values, matrices S to this kind of form, this quadratic form, and then we can learn more about this matrix S by looking at what their resulting polynomial and what the resulting graph looks like. So now we're kind of flipping what we were doing on its head, and now we care more about this matrix S. And now we're kind of just using quadratic form as a tool to learn more about different matrices S. And that's actually how we kind of classify these 5 types of symmetric matrices based on their behavior when put into this quadratic form. So let's go through all 5 of these. It's kind of going to go from slowest to quickest because we're kind of going from the most important to the least important. So we'll be starting with the positive definite matrix. So I'm going to do this over here. I know it'll be kind of off screen, but yeah. All right, so let's start off with the titular positive definite matrix, which is arguably the best one out of this 5 because it has some nice properties. It's the one we're going to be spending the most time on. Well, first of all, how do we classify some symmetric matrix S as being positive definite? Well, it's to do with that quadratic form again. So if we put it into quadratic form, so some x transpose Sx, and remembering that this evaluates into some quadratic form polynomial, we know this matrix S is going to be positive definite if this quadratic polynomial is greater than 0 for all values of x, except for x equals 0. We don't include that. Notice that it's greater than and not greater than or equal to. That's important. So imagine that this S was like 2 by 2, so this would evaluate into some binary quadratic form polynomial, so something that looks like ax squared plus bxy plus cy squared. Then this polynomial, so these a, b, and c values come from this matrix S. Then this quadratic polynomial would have to be greater than 0 for all values of x and y. But notice that when x and y equals 0, which is this case here, this evaluates into 0 because all the terms get zeroed, and 0 plus 0 plus 0 gives you 0. So that's basically kind of, you can think of this quadratic polynomial as being the quadratic polynomial of this matrix S. But let's think of things graphically, because that'll help out. So let's graph this quadratic polynomial when S is positive definite. When S is positive definite, we know that quadratic polynomial has to be greater than 0 for all values of x and y except for x and y equals 0. So that's going to look like something like this. So we can draw it in 2 dimensions. It's going to look something like this. It's going to look like some paraboloid centered at the origin with its minimum at 0. Because it's going to be positive for all values of x and y, so x and y. It'll be positive for all values of x and y. And it'll be equal to 0 when x and y equals 0. So it'll have its minimum at the origin. So that's just kind of, you can think of this paraboloid as being the paraboloid created by a positive semi-definite matrix. You can think of this as a positive semi-definite matrix's paraboloid. But the thing is that having this graphical intuition becomes kind of unhelpful when your S is bigger than 2 by 2. Because if we only relied on this graphical intuition to classify a matrix as positive definite, or it's the other 4 that we're going to be talking about, then after S goes over being 2 by 2, you can't graph it anymore. So at 3 by 3, you can't graph the paraboloid of a 3 by 3 symmetric matrix. So at that point, we generally say that you can classify some matrix as positive definite if all of its eigenvalues are positive numbers. So the more general way and the more less graphical and more kind of practical way of knowing if a matrix is positive definite is all eigenvalues are positive. So none of them are equal to 0. They're all greater than 0. So all eigenvalues are positive. But I said we like these, but it's still not really clear why we like these. But the big, important, huge thing with positive definite matrices, what makes us really love them in computations and that sort of thing, is that they're guaranteed always to be invertible. And this will really play a big role in the lecture later on in 2.9 for the Moore-Penrose pseudo-inverse, which is a much more complex topic, but still uses this idea. It'll become really important then, and a ton of other things as well. So always invertible, that's important. That's the nicest thing about these. So it's always invertible. That's awesome. Great. That's why we like them. Okay, so that's all we had to say about positive definite matrices. So that was the graphical intuition, that was that, we got everything. But now we're going to deal with maybe the less liked kind of cousin of the positive definite matrix, which is the positive semi-definite matrix, which sounds very similar, but is actually a whole world different. Well, let's make a divide here. I'm changing colors. I'm going to get a nice color gradient here. All right. So positive semi-definite matrices, they sound very similar, but why don't we like them as much? Positive semi-definite. Put semi-def for short. First of all, when is the matrix S positive semi-definite? And you'll see they quickly fall into a pattern. So if we put it into quadratic form, if you put some matrix S into quadratic form, the matrix S is positive semi-definite if this resulting quadratic polynomial is greater than or equal to 0 for all x. And then except leaving out x equals 0, so x is not equal to 0. All right, so we can notice that's very similar. The only difference is that now we allow this polynomial to evaluate to something that does equal 0, even when x does not equal 0. So let's go straight to the graphical intuition here, and then we'll explain why this graphical intuition makes sense. So let's draw this 3D graph, and we're going to have another thing here. So now instead of it being a bowl, it's going to look something more like a taco in 3D space. So something like you can imagine holding a taco, it's going to look like that. So let's try to draw that. So it's going to look something like this. It's going to look something like this. Something like this. Like that in space. So kind of like a taco type thing, like a wrap being held in space, like this. And the main difference here is that we used to have one minimum here, right at the origin. But now we have a ton of minimums. In fact, an infinite amount of minimums. And that's because now we allow this quadratic polynomial, which is represented by this graph, to equal 0 for more than just x equals 0. Before x could only equal 0, and that's when the whole thing would value to 0, when x and y equal 0. But now x and y can equal a bunch of other values, and it can still value to 0. So that basically means that we have an infinite amount of minimums. So it's going to look something like this as opposed to a bowl, because it's going to have its kind of minimums kind of going to drag. You can think of it as kind of being a long minimum, because there are multiple values of x and y that get us to 0. All right, but again, we don't want to rely on this graphical intuition, so we use the eigenvalues again. So in this case, a matrix is positive semi-definite if its eigenvalues are all positive, but some might be 0. So all of the eigenvalues are greater than or equal to 0. So all eigenvalues greater than or equal to 0. So notice that's the difference. We got greater than, now we have greater than or equal to. But the nasty thing here is that it's never invertible. The only case when a positive semi-definite matrix is invertible is when all of its eigenvalues are positive, which means that the only case when a positive semi-definite matrix is invertible is when it's positive definite. So when not all the eigenvalues are greater than 0, so when some eigenvalues or one eigenvalue is equal to 0, then this is uninvertible. And I won't say why, but you can Google it later. So I'm going to say, so uninvertible. going to say uninvert. You can't invert these unless they are a positive definite matrix. Because you can think of positive semi-definite matrices kind of being a subset of positive definite matrices. So positive semi-definite matrices, not as nice. They don't have that nice property, so they're kind of useless to us. If we have a positive semi-definite matrix, we often want to see how we can turn that into a positive definite matrix and thus make it something that we can invert. Okay, so now we're going to kind of move on to the weirdo middle child of this matrix family, which is the indefinite matrix. So I'm going to do this in green. So the indefinite matrix. So this is a weird one, and it's probably the least important, but I'm going to tackle it just for sake of completeness. So indefinite. So maybe you can kind of guess where this is going already. When some matrix is indefinite, when some symmetric matrix S is indefinite, you have this thing where X transpose SX is greater than or equal to 0 for some X, and then it's X transpose SX is less than or equal to 0 for some other X. So kind of shortly, X transpose SX can be positive or negative or 0 or not. There's no kind of predictable thing. It's like, oh, it's all positive or it's all positive or equal to 0. It can be equal to anything. It's a wild card. And the graph of this, and I'll have a hard time drawing this, but it's something that's a little wacky. It's basically some kind of parabola shaped thing. It's not even a parabola anymore. It's some curve in space that goes up in some directions and down in some directions. So you're going to end up with something called a saddle. And maybe I'll show a picture on the screen right now because I won't be able to draw it. That's what a saddle shape looks like. So it's going to be a saddle kind of centered at the origin. So you're going to have some parts of the saddle are going to be pointing downwards in some axes. And in some axes, you're going to be pointing upwards. So you're going to kind of end up with this saddle shape that, this image right in this middle here. So that's what you kind of think about graphically what an indefinite matrix is. And maybe you can kind of predict here, the eigenvalues in this case can be positive, negative, or 0. So eigenvalues are positive, negative, 0. I don't even know how I say this, so I'll just say anything. Not really, I guess, because the eigenvalues must be, a mix of positive, negative, and 0. A mix of positive, negative, and 0. Hopefully you can kind of get that from there. So they're a mix. And the invertibility of this is kind of unknown. Sometimes they might be invertible, sometimes they might not be. But the thing is, if there is a 0 in their eigenvalues, it is uninvertible. And that's kind of the general thing here. I'm not going to prove it again because this is just a review for this machine learning course, so I'm not really doing too many proofs. But the general rule is if you have an eigenvalue that's equal to 0, your matrix is uninvertible. So if it's just positive and negative mix here, then it's maybe, right? But that's going to be indefinite, and the reason why they're not really helpful is because we can't really be sure of anything, right? Because with these, even though this one's not as good as this one, we're kind of sure of some stuff here, but this we don't even know. So it's not really that important, but it's good to know when people say indefinite matrix, that's kind of what they mean. Okay, so now we're going to go into the negative matrices, and this is going to be really quick because they're going to basically be just exactly this but reversed. So now we're going to go into the negative semi-definite matrix. So we can kind of follow an arc from most positive to most negative. So we're going to go to the negative semi-definite matrix now, which I think you can probably even already conceptualize in your head. I'm just going to write down here for secrets. So invertible, and then I'll put a question mark to tell us that we don't know if it's invertible or not. Okay, so now we're going to go to the negative semi-definite matrix. Sorry. Look at all the colors I have. I'm just kind of flexing my colors. All right, so now we're going to go to the negative semi-definite matrix, and I'm going to go fast through these lessons because they're basically like this, and you can already kind of have what they look like in your head, but I'm just going to clarify. All right, so negative semi-definite. Negative semi-definite. All right, so I'm going to put that for short. So negative semi-definite. So basically, it's going to be X transpose SX for some symmetric matrix S. S is going to be negative semi-definite if it is less than or equal to 0 for all X, except when X equals 0, so not when X equals 0. Oh, and I forgot here, Here, when x equals 0, you can still be sure that it will be 0. So when x and y and all your variables equal 0, you're still going to have a 0 there just because what a quadratic form polynomial looks like, which we covered in the last lecture and maybe the beginning of this one. So, okay, back to here. So negative semi-definite matrix. So we know a matrix S is negative semi-definite if we put it into quadratic form and it's less than or equal to 0, this polynomial, for all values of x except for when x equals 0. Because when x equals 0, then everything equals 0. All right. Great. So let's draw the graphical intuition of what this looks like. Just quickly. It's basically going to be an upside down taco. So we have this taco here, right? So now we're going to have an upside down taco, which looks, it's the physically implausible taco, right? Something that looks like this. I don't even know. Something like that, right? So kind of a taco where the maximum now is 0. And the maximum lies all along the xy plane. Right, because before the parabolas that we were creating all had minimums. Because this one had a minimum here, this one had a minimum infinitely, this one, I don't even know. But this one, and we'll see with the negative definite matrices, now we're dealing with paraboloids with maximums. So you can see that the maximum of this is infinite. There's an infinite amount of maximums, and those maximums are when it evaluates to 0. So now we're seeing that for multiple values of x and y, you get the maximum of 0. So there's an infinite amount of maximums in a negative semi-definite matrix. And we know a matrix is negative semi-definite generally if its eigenvalues are less than or equal to 0. So eigenvalues less than or equal to 0. All right. And remembering that I quickly mentioned that if the eigenvalues of a matrix are 0, or if at least one of a matrix's eigenvalues are 0, then it's uninvertible. So generally, negative semi-definite matrices, if you have some eigenvalue that's equal to 0, they're uninvertible. So generally, they're uninvertible. Uninvertible. What a weird word. Great. Okay, uninvertible. Finally, we can move on to our last one. I'm not going to have fun erasing this. It's so pretty. Okay, so now we're going to go on to negative definite, which are doing a nice negative red. Okay, so negative semi-definite. Negative definite. And I'm going to go quickly because I think we already know what this is going to look like. Negative definite. So basically that's when you have some symmetric matrix S and you put it into quadratic form. And this polynomial is going to be less than 0 for all x. Of course, x except for when x is equal to 0. And the resulting thing will basically just look like that, but flipped. So now you have the maximum at 0. So it's going to look something like this. So now it's going to look like a bowl that someone flipped over. Maybe they were angry. And now we're going to have something that looks like, looks like this. Something that looks like that. So that's going to be your graph of your negative definite matrix. And finally, just to round this out, that's when all the eigenvalues are negative. Strictly negative. And that means, since in this case you're going to have no 0 eigenvalues, your negative definite matrices are also, like the positive definite, are actually guaranteed to be invertible. So that's nice, right? Even though it says negative, you got some positives, right? Invertible. All right, so that's it. Those are the 5 classes of symmetric matrices. You'll see here, it's like the rainbow. It's very nice. And I guess the summary here is that we like the definites, because those are invertible. We like the positive definite just because it has a minimum, and that's kind of a nice thing later on as opposed to a maximum, but we don't really need to talk about that here. And then positive negative semi-definite are always uninvertible unless they are a part of the negative and positive definite matrices. And indefinite is just weird. Like I don't know. We don't know with that one. All right, so that's it. That's all of the matrices. Those are all 5 types of the matrices. Hopefully you haven't fallen asleep. But yeah, thanks for watching. This will come in handy, promise, in especially the pseudo-inverse lecture in 2.9. So I'll see you there. Bye.